Alrighty. Waves through mediums. Oh, sorry. That's the end of the notes. Types of waves. There we go. Now I want to start over. Oh. So transverse waves. This is the one we've been looking at already. All right, so particles vibrate at right angles to the direction of the travel of waves. So if you look at this little animation here, you can see that you have the individual particles. These represent the particles that are transmitting the energy of the wave. The wave is actually starting here, and it travels this way across. So it's going left to right. But if you look at any one of these individual particles, they're just moving up and down. So their movement is perpendicular to the direction of travel of the wave. So they just move up and down, and they don't go anywhere. They stay in that location, just moving up and down. And this is the type of wave that has crests and troughs. So if you look at the board here, drawn a real basic one, and if we labeled it just really quickly, you've got your wavelength going from crest to crest, trough to trough, or where the wave repeats. So that's lambda. You have your amplitude from rest to its maximum, and you can measure that from either to a crest or to a trough. So that's your amplitude. And which one am I missing? Oh, and then frequency is you count it how many times it would travel past a point per second. All right? So this is a fun one. Longitudinal waves. This is the one that Julia's group made with their Slinky. Picture at the bottom. This picture, you mean? Like the animation? A little bit. So longitudinal waves, also known as compressional waves. The particles vibrate parallel to the direction of travel of the wave. And they're made up of compressions and rarefactions. Now again, if you look at the individual particles in this animation, you'll see that they're going in the same direction as the waves. So the waves are traveling left to right, the particles are moving left to right, but, and this is going to make some of you upset, pick any single one of these particles and you'll see that, again, they don't move with the wave, they just move back and forth. So pick any single one. So this one right here. Back and forth, back and forth. Pick any other one. Back and forth, back and forth. So if you watch it for a while, you'll see that all it does is move back and forth. None of those particles are traveling from the left-hand side to the right-hand side. None of them are disappearing. None of them are reappearing.
It's an illusion.
That is so weird. No, they are moving.
No, just back and forth.
Back and forth.
Pick any particle, Annika.
So why?
All right, so now labeling the parts of the wave here. This is a real basic sketch of a wave, a compression wave or longitudinal wave. Now, if you want to know what the wavelength is, well, for the transverse wave, it was from where it repeated. So we went from crest to crest or trough to trough. What do you think it's going to be for longitudinal? Where it compresses or where it repeats. So we have a compression here. The next compression occurs over here. So that is our wavelength. Yeah. So it's from one compression to the next is your wavelength. Now, your amplitude, or how loud you make it, if you're talking about like a sound wave, also is basically your wavelength. It's how far the particles will move back and forth. Now, because longitudinal waves are a little bit difficult to interpret, often what you'll see is they'll convert longitudinal waves into a transverse wave for visual representations. So how many of you have seen sound waves and it looks like a regular wave, whether it's in a movie or if you're looking at any sort of thing? We'll actually look at some sound waves. And what they often do, they'll convert it into a transverse wave, even though sound waves are actually compression waves. So they're longitudinal waves that are produced by whatever's making the sound. So it's something vibrating back and forth, just like the red bar is over here in this animation. That's how sound waves work, but they're hard to interpret. So what happens is when we want to visualize it, they'll often change it into a transverse wave. Surface waves. This is kind of like your ocean waves.
It's kind of like a combination of two, actually.
It is.
Because they're not actually. They're not actually moving. Can we spell what's called it?
Surface waves. These occur at the boundaries between two media, so at the surface of water. Particles have a combined longitudinal and transverse motion. Basically, they move in a circle. So if you pick any one of these particles at the top, and you can see it's moving around. What happens when I draw on this? Just moving around in a circle. These particles at the top. The blue one really shows it well. That's why they made one blue. Now, obviously, as you move away from the surface, further down, you don't get this motion as much. I mean, if you've ever gone swimming in the ocean, you're playing in the surf. If you don't want to get hit or knocked over by a wave, you just duck under it. And if you're this much below the surface, you barely even feel the wave. So that's...
below the...
Yeah. For 1 second. So silly little game. We're going to do it right now. Yay, we got 8 out of 8. Good job. These are the answers. So interference. Now, just to quickly explain this animation, you have the large wave starting on the left, and then it travels to the right. When it hits the right-hand side, it's not reflecting back and forth. What they're doing is they're just playing looped this animation. So the big wave starts on the left, it goes over to the right, and then the animation restarts with the big wave over at the left and goes to the right. So it's not showing reflection at the two ends. It's just showing the interference. So the small wave starts to the right, moves towards the left, and then the animation restarts. Okay? So two waves can interfere in such a way to produce points that don't seem to move at all. These are known as nodes, and all other points have the maximum displacement. Those are the antinodes. So this one here shows it. So you got the waves, they're moving towards the right, and then they're going to reflect off the y-axis here. So as they reflect and move back, so this crest is going to move back. You can see it cancels out, and then it increases the amplitude. This is interference. Yeah. So you girls are actually doing this with the slinkies. You just have a natural tendency to try and find a standing wave. So you can see how these points here don't move. They don't seem to move. They seem stationary. So, well, this is just the wave moving towards the barrier. It's a wave.
What's that?
Well, this is now the first part of the wave that when it hits that barrier, it reflects back. So now it's reflecting back upon itself, but the wave is still moving in both directions. So you have the wave moving down towards the y-axis, and then you have the reflection moving back against it. And that's how you produce a standing wave like that. So this last animation here girls. Last animation here shows the reflection already happening. So you can just see that the nodes are marked in green, and the antinodes would be the maximums here. So this point here doesn't appear to move.